All right, guys. Hope you had a nice weekend, and welcome to your FID day lesson. It's my second time recording this because the first time, a little bit of an error, and the sound didn't record. So hopefully you're hearing this one. As we kind of move away from what we were talking about with probability, we're going to be using those ideas to tie it back in our next unit and look at data analysis. When we see what's happening in our sample, how sure can we be that that's truly what's going on in the population as a whole, right? We talked about how this is like one of the important ideas of statistics is be able to have that certainty that what we see in our sample isn't just some quirk, that this is truly what's going on in our population, because that's what we truly care about. So we're going to be using a couple ideas. This law of large numbers directly comes from probability. We said how probability is meant for the long haul. It's meant for the big picture. So what this law of large numbers does is that it allows us to say that our sample, it's the small case. But if we were to extend that across over time and large enough samples, and we were to repeat this over and over and over again, that it becomes pretty much a certainty that this is truly what's happening in the population as a whole. And we'll kind of end today looking at this central limit theorem, which is really one of our most powerful ideas in statistics that allows us to say that things from our sample, whether it fits a normal distribution or not, when we're looking at the big picture, that this is truly going to fit a normal distribution based off of all of our samples. Okay, so we'll expand on what that idea means later on. One thing that's important to remember is that because we're distinguishing between our samples and our populations, we've talked about the differences in the notation. Well, we also have differences in the vocabulary here. A parameter is what we're talking about with the population. It describes the population. The value of a parameter is not known because we're not taking a census. We're not looking at the full population. But that's really, ideally, what we'd like to be talking about. Now, a statistic is taken from the sample. Okay? We're not making use of any unknown parameters. Now, in practice, it says we often use a statistic to estimate an unknown parameter. Okay? So, the easy way to remember this, think of S&P. Statistics comes from samples, and parameters come from populations. So, we had already said that with our notation, we know that this Greek letter mu represents our population mean. Okay? And similarly, this lowercase sigma represents our standard deviation for the population. So those are parameters. Okay? Now, we will be taking samples, and each of our samples will have its own mean. So our sample mean is x bar, and the standard deviation of our sample is lowercase s. Okay? And again, we want to, in the big picture, know how well our sample represents what's happening in that population as a whole. Yeah. So this process of statistical inference, it involves using information from a sample to draw conclusions about a wider population. And we know that there's going to be some variability and some variation in our samples. We don't necessarily get a 100% accurate reflection of the entire population with our sample. There's some variation. We've talked about this with respect to like coin flips. We expect 50% heads, but there's no guarantee that we flip a coin 10 times, we get exactly 5 heads. There's some natural variability. Well, the same thing happens when you're taking a sample. There's no guarantee that it's automatically going to be reflective of that entire population. We can think of a statistic as a random variable. It takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its probability distribution using what we've learned in our previous unit. Now, what this law of large numbers says, because probability is meant for the long haul, it's meant for the big picture, what the law of large numbers will say is that if we keep taking on larger and larger samples, the statistic x bar is guaranteed to get closer and closer to that parameter mu. Okay? So we take that sample statistic and it becomes that parameter value. And we know that what's happening in the small case should become what's happening in the big picture across the long haul. So it's important to keep in mind the differences between what we talked about earlier in the year with a population distribution and the sampling distribution that we'll be looking at in this unit. When we were looking at the normal curve before and doing z-score calculations and things like that, we were looking at the entire population and where does an individual relate to the population as a whole. We had our mean right there at the center, mu, and we can count standard deviations to the right and the left. And it gives you an idea of how an individual falls with respect to the entire population. Now with a sampling distribution, we're using our statistics to indicate where all of these possible samples fall in relation to the population. Okay. Now we have a note here on the bottom. It says be careful. The population distribution describes that the individuals that make up the population. A sampling distribution describes how a statistic varies in many samples from across the population. So essentially what's happening is we're taking a bunch of samples and we want to see the model and the distribution of all of these samples. Here's an idea. Let's say that we have a 50-50 chance for red and blue with a color selection. We know that the population parameter is 50%. Okay? Very similar to a coin flip. So we're going to take a bunch of samples of size 20, and on our first sample of 20, we only get 8 out of 20 as red. Okay? A little bit below what we would think. Our second sample of 20, we get 11, so pretty close to what we'd expect, but a little bit above. Our third sample, we get even higher above, 13 out of 20, 65%. But across the big picture, if we were to take a bunch of these samples of size 20 over and over and over again, we would expect them to fit in this distribution, where most of our samples are going to be 10 out of 20, 50%. Some are a little bit higher, some are a little bit lower. Very few are extremely high, very few are extremely low, but the distribution of our samples, hence the name of our lesson here, sampling distributions, should fit this normal curve. Let me give you one more example and we'll kind of wrap up and end with this. Let's say that there is a large national weight loss clinic that lasts for 10 weeks. Now, unknown to us are those population parameters, okay? But across the entire nation with this weight loss clinic, there is a mean weight loss of 8 pounds and a standard deviation of 5 pounds. Okay? That's what's happening across the entire population. Now, we could use our empirical rule to kind of visualize this population distribution. Okay? Our average weight loss is 8 pounds right there in the center, standard deviation of 5 pounds. So within one standard deviation, we have 3 pounds of weight loss to 13 pounds. Take it out another standard deviation. Okay? On the upper end, we have 18 pounds, 18 pounds of weight lost. On the lower end, we have negative 2 pounds of weight loss, which actually means they're gaining 2 pounds. Okay? Within 2 standard deviations on this normal curve, we have 95% of our data. So we'd expect 95% of the participants in this weight loss clinic to lose between negative 2 pounds, gaining 2 pounds, and losing 18 pounds. Now, we can't measure every single person. We don't want to take a full census. So instead, we're going to take a bunch of samples of the same size. And in this case, 25 is our sample size. So we see some possible samples up here, samples 1, 2, 3, and 4. Now, each of those samples has their own mean. These are sample statistics. This is an X bar. And each sample has its own standard deviation. Okay? This would be S. And we can see there's some variation. None of them perfectly match our population parameters of 8 and 5. However, you can see that they are pretty close. Okay? We have our first sample a little bit above for our mean. Standard deviation is a little bit less spread out, 4.74. Okay? But our second sample, that mean is much lower. Okay? Again, it's less spread out. So we have a lot of values that are on the low end here. Okay? But then in sample 3, much higher mean, 8.48, and it's more spread out. Okay? Look at that sample 3. We have some people gaining 4 pounds, and we have other people losing 18 pounds. There's a lot of variability there. Same thing with sample 4. Okay, negative 3 to 19 would be our range, but we have a lot of variation going here. Now, what we're going to be working towards is saying that, well, none of them perfectly match, but across the big picture, okay, all of these sample means should approach that population parameter of 8. And all of these standard deviations, well, they're not going to be the population standard deviation because we would expect less variation in our sampling distribution. So we have a rule here that says that all of our sample means, X bar, should approach and become that population parameter, mu. But the standard deviation for this sampling distribution should be identified as our population standard deviation sigma over the square root of n, our sample size. Okay. We'll expand on exactly what this means a little bit later on when I see you on Wednesday. We'll talk about how these sample means kind of fit together to fill out that distribution. We'll look at some simulations of this and talk about where these equations come from. Okay? But this is a good jumping off point for today. So if you have any questions, you can log into my office hours from 11 to noon. Otherwise, I'll see you Wednesday. Have a good